Hello and welcome. I am Dr. Pauline Fu. In this video, I will present hypothesis test for population standard deviation. In the previous lectures, I presented hypothesis test for a population proportion. We used z-test. I also presented hypothesis test for population mean. We use the t-test. Now I will present hypothesis test about population standard deviation. In this session, I will introduce a new concept, chi-square test. Suppose you have a simple random sample. Size is n. This simple random sample is obtained from a population having normal distribution with mean is mu, and the standard deviation is sigma. Okay. If you use sample size -1 times sample variance, remember S is the standard deviation of a sample. S squared is the sample variance over population variance sigma squared. And this distribution we call chi-square distribution. It is with n-1 degree of freedom. Okay, S squared is the sample variance. Sigma squared is the population variance. The characteristics of chi-square distribution. Chi-square distribution is not symmetric. Actually, chi-square distribution similar like something like this. This is chi-square distribution. Okay. And the shape of chi-square distribution depends on the degree of freedom, just as student T distribution. Okay. If you have different degree of freedom, you may get a different distribution. Okay. Number 3, as the number of degree of freedom increase, chi-square test distribution becomes more symmetric. Okay. The value of chi-squares are always positive number because by definition, chi-square is a square over square. So the result of chi-square is always a positive number. This is a graphical representation of a chi-square test with a different degree of freedom. Okay. So the blue line, if you have a chi-square test, degree of freedom is 2. Okay. And this one, degree of freedom is 5, degree of freedom 5, and then degree of freedom is 10. Okay, and degree of freedom is 15. As you can see, as you increase degree of freedom, the distribution is more symmetric. When we do the test about the population variance or standard deviation, we use those steps. The sample obtained from using the simple random sample or from a randomized experiment. And we also assume population is normally distributed. In step 1, you always state the null hypothesis and the alternative hypothesis. Here, we test a claim about a population standard deviation. So we are saying sigma equal to some hypothesized number. For example, sigma equal to 2 or sigma equal to 3.5. Alternative hypothesis, H1, sigma not equal to a hypothesized number. For example, sigma not equal to 2 or sigma not equal to 3.5. And this, if you have H1 has not equal sign, it is a two-tailed test. And when you have two-tailed test, remember this is chi-square distribution. So two-tailed test like this. You have two tail. One tail is here, and the other tail is here. So left-tailed test. How do we know it is left-tailed test? Usually you have keyword decrease, less than. So H1 is smaller than. But H0 always maintain equal. Okay. So left tail test for chi-square, you just have a little left tail here. This is a picture of left tail test. And next is the right tail test. H1 is greater. From the context, you will also get the hint. The keyword such as more than, less than, more than, greater than, that is a right-tailed test. H0 maintain equal. Okay. So if you have right-tailed test, it is just this right tail here. Okay. Step 2, select the level of significant alpha. Okay. Usually it is 0.05. Step 3, calculate test statistic. Remember test statistic, it is just a formula. And this formula said, use sample size n minus 1 times sample variance over population variance. Okay. Once you completed the first 3 steps, and then you can use either classical approach or p-value approach. Now, let's look at classical approach. Okay. You need to use a table to get the critical value with n minus degree of freedom. Alternatively, you can use Excel to get degree of freedom. Okay. For example, so I'll delete this one. The chi-square test, critical value, CHISQ, okay, dot INV. INV means critical value, okay, and the probability, for example, 0.05, that is alpha. Degree of freedom, for example, it is 2, okay, and you get this number, critical value, okay. So that is how you use chi-square test, chi-square, to get the critical value. This is a graphical representation where, oops, just try to move the window. You have a two-tailed test. Okay. When you have two-tailed test, each tail, the area for each tail, it is half alpha. Half alpha represents the area. And this point represents the critical value. This is a critical value. Because chi-square test is not symmetry, those two critical values are not equal. Okay. Actually, that both have positive numbers, but they are different. It is not like in normal distribution. If you have one critical value is 1.96, because of the symmetry for normal distribution, you have another critical value, negative 1.96. That is for normal distribution, but that is not for chi-square. Okay, I repeat, the two critical values for chi-square are different. If you have just left tail test, you just have one critical value. Okay, and this area is alpha. Okay, and the area, this one here, is 1 minus alpha. 1 minus alpha. Okay. So if you have a right-tailed test, the critical value is subscript alpha chi-square. Whereas when you have left-tailed test, the critical value we labeled chi-square 1 minus alpha as a subscript. Okay. So the area always refer to the right of the critical value. See, 1 minus alpha. This one is 1 minus alpha. This shaded area here. Okay. And here, the area to the right of critical value. So this is alpha. That's why I use subscript alpha. And then, classical approach step 4, compare step 3 test statistic with a critical value. Okay, with critical value. On this picture here, if the test statistic is here, that means test statistic is in the rejection region. You reject H0. If test statistic is here, or is here, test statistics are not in the rejection region. So you do not reject H0. And in this left tail test, if test statistic is here, you reject H0 because test statistics in the rejection region. Critical region is also called rejection region. If test statistic is here, or even here, you do not reject H0. Okay. And this is a right tail test. If test statistic is here, you reject H0. If test statistic is here, you do not reject H0. Okay. So this is in table format. We introduced classical approach, now p-value approach. When you did step 3, you calculated the test statistic. Okay. Once you have this test statistic, and then you found the p-value. What is the p-value? P-value is the area corresponding to test statistic. Suppose this is chi-square distribution. Okay. And suppose this is a two-tailed test. So you have one tail, another tail. Okay. And the p-value is this area, and suppose this is test statistic. It is like in chi-square test, most often it is right tail test. So I'm just going to illustrate. So suppose this point is a test statistic. Okay, test statistic. And the area to the right, this one here, is a p-value. So p-value is the area corresponding to test statistic. When you have, I explained right tail, when you have left tailed test, p-value, this is p-value. P-value is the area corresponding to test statistic. Okay. This is the left tail test situation. Okay. See, we usually do not have a two-tailed test situation. Usually it is most often it is right-tailed test when we use chi-square test. Be careful, the procedure for chi-square test for population standard deviation is not robust. Okay. Therefore, analysis of data indicates that variable does not come from a population that is normally distributed. The procedures presented here are not valid because it is not robust. You have to make sure the population is normally distributed. If the population is not normally distributed, you cannot use this chi-square test for population standard deviation. Now let's look at an example. A can of 7-Up states that the contents of the can are 355 milliliter. A quality control engineering is worried that the filling machine is miscalibrated. In other words, she wants to make sure the machine is not under or overfilling the cans. She randomly selected 7 cans of 7-Up and measures the contents, and the following data present the data. Remember in section 9.2, we assume the population standard deviation was 3.2. Okay, assume. We just given assume. Then you are asked to test the claim that the population standard deviation sigma is greater than 3.2. Use alpha 0.05 level of significance. Okay. Here, you see the keyword greater than. That means H1 must have greater sign. Okay. So let's do the steps. Step 1, state the null hypothesis. Population standard deviation equal to 3.2. Alternative hypothesis, greater than 3.2. Why? Because the keyword greater than. Step 2, set alpha 0.05. And step 3, plug in the formula for chi-square test. The formula said sample size minus 1. Okay. Sample size minus 1. Sample size is 9. 9 is sample size. Okay. Times standard deviation squared, sample standard deviation. And how do we know this standard deviation is 3.464? Okay. Based on this data, you plug in your calculator or plug in under Excel. You can calculate standard deviation. The result is 3.464. And population standard deviation is given 3.2. That is the population standard deviation. So you get result chi-square 9.374. And once you get this one, you need to find the critical value. You can go to the table to find the critical value. And I introduced Excel. In Excel, you type in equal chi-square dot INV. Because this is the right tail test, you have to use dot RT. And plug in alpha is and the degree of freedom 8, you get 15.507. So I'll show you on the Excel. Okay. Where's my Excel? It is here. So I'll use the cell here. Maybe I want to increase the cell size. equal chi-square dot inv dot rt. Probability is the alpha, 0.05. Degree of freedom is 8. Okay, and then press enter key. You get 15.507. Okay, you get critical value. So this is the formula in Excel. Now you have the critical value. When you have critical value, remember critical value decide rejection region. Okay, so let's say this is the critical value, this point, 15.50, 15.507. If this is a critical point, this one is the rejection region or critical region. So rejection region or critical region. Now, where is test statistic? 9.374. If this is 15, 9.374 must be smaller than 15. It is here. Obviously, critical value is not, test statistic is not in the rejection region. So do not reject H0 or fail to reject H0. So go back to H0. Do not reject H0. Okay, H1 and H0, one of them is correct. So your final conclusion, the population standard deviation is 3.2. So this is a classical approach. Compare critical value with the test statistic. Now let's do the p-value approach. P-value approach. For p-value approach, we need to find what is the p-value. Remember, p-value is the area corresponding to test statistic. And remember, our test statistic is 9.374. So p-value is the area to the right of test statistic. This area is a p-value. This area is a p-value. And then how do I find this area? Okay, so again, you can use the table. I try to use Excel. Okay, so I go to chi-square dot dist, and this is right tail. Okay, so x is 9.374. Degree of freedom is 8. So I get p-value 0.311. Copy this. Okay, and this result I get so they are equal. So this and this is p-value. Okay, obviously this p-value greater than alpha. When p-value greater than alpha, do not reject H0. See, we get the same conclusion using p-value method with using classical approach. Okay, so this is the p-value. Okay, so this guy is the p-value. And this example is a typical example about hypothesis test for population standard deviation. So final step 5 is conclusion. There is insufficient evidence at 0.05 level of significance to conclude that the standard deviation of the can is greater than 3.2. Okay, not sufficient evidence to conclude it is greater than 3.2 means you actually reject H1, so you have to accept H0. Okay, in other words, the population standard deviation is 3.2. So far, we did test for population proportion. We did test for population mean, and now we did test for population standard deviation. So if you put them all together, for population proportion, we use z-test. This is test statistic. For population mean, we use the t-test. And for population standard deviation, we use chi-square test. Okay, so I just try to increase this summary part so that you see the formula clearly. So that is we did 3 tests. Okay. All right. In summary, I did hypothesis test for population standard deviation. I used 2 approaches. One is a classical approach where I compare critical value with test statistic. The other is a p-value approach. I compare p-value with alpha. In both situations for the example given, we conclude do not reject H0. Okay, and I also summarized the 3 different tests we have done so far: z-test for proportion, t-test for mean, and chi-square test for population standard deviation. Hope you learned something from this lecture. Thank you so much. See you next time.